Hello there and welcome back to the Sleep Science. Tonight you drift with me into the great dark ocean above your head, where stars whisper and shimmer as though each one were a candle stuck to an infinite ceiling. You lie back, weightless, your breath slow as the first lights of the universe blink awake. Imagine the cosmos as a newborn room, utterly quiet, utterly simple, only two toys rattling around: hydrogen, the lightest fluff ball, and helium, its slightly heavier cousin. Nothing else yet. No gold rings, no iPhones, not even a speck of the calcium that will someday harden your teeth. Just a chill soup of hydrogen and helium atoms stretching in every direction, waiting for something more interesting to happen. And here's the reality check. If you had appeared at that time, you probably wouldn't survive longer than the first breath. No air, no warmth, no cozy bed. Just endless thin gas, colder than the worst freezer aisle. The only light is faint, left over from the Big Bang glow stretched thin and red. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And if you're tuning in from your couch, or curled up in bed, drop your location and local time down below. I love to see our little community of sleepy scientists mapped across the world. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You float among those first atoms. They're drifting lazily, bouncing against one another like shy strangers at a party where nobody brought snacks. For nearly 400 million years, nothing more dramatic than expansion happens. It's the longest waiting game in history. Yet gravity, always the quiet schemer, tugs and nudges. Where gas is slightly denser, gravity pulls harder, gathering hydrogen clouds like lint rolling into a ball. Historians still argue whether the very first stars lit up in neat little clusters or if they flickered solo, like lonely porch lights in the void. Picture it. A dark stage, curtains drawn. Then, with a slow squeeze, a clump of hydrogen condenses until its center glows faintly. That's the first spark of starlight. If you were floating nearby, you wouldn't just see it. You'd feel a thin wash of warmth, like the tiniest candle in an endless cave. And even though it's just hydrogen bumping into hydrogen, the crowding creates heat, and heat builds pressure. The gas resists collapse, but gravity keeps insisting closer, closer. This is the awkward teenage phase of a star. Too hot to stay quiet, not hot enough to ignite. Astronomers call them protostars. They puff and sputter, cloaked in dust, glowing red through cosmic swaddling blankets. You can imagine them sulking in their nebula bedrooms, thinking about their destiny. Some never quite make it. Too small, they fade as brown dwarfs, failed stars that glow dimly like dying coals. A quirky tidbit here. Some of those brown dwarfs actually rain molten iron, which sounds more like a heavy metal album cover than a weather report. But when a protostar is large enough, gravity finally squeezes its core into something astonishing. The hydrogen atoms, usually polite about their personal space, are rammed so tightly together that their electrons scream, "We can't hold back anymore." Nuclei merge, fusion ignites. Suddenly, the star isn't just hot, it's a furnace. That first fusion flare is the universe's equivalent of plugging in the oven for all future recipes. And what an oven! The light released is so strong it pushes back against gravity itself. The star stabilizes, like a tightrope walker holding balance with a fiery pole. If you could listen closely, it would sound like a deep, steady hum, a cosmic heartbeat pulsing through space. That rhythm has played on for billions of years in countless stars, shaping everything you'll ever touch. Meanwhile, here's a historical note. In 1920, Arthur Eddington boldly suggested that stars shine by smashing hydrogen into helium, long before anyone could prove it. At the time, critics scoffed. Imagine claiming the sun is basically a giant hydrogen bomb politely burning at dinner candle speed. Yet Eddington was right, and his hunch unlocked the key to cosmic alchemy. So here you drift, watching the first stars ignite like lanterns in a cavern. They don't last long, massive and hot. They blaze out in a few million years, while smaller ones linger for billions. You know the endgame. They will cook elements, spill them into space, and set the stage for every bone, ocean and tree. But for now, just feel that newborn light warming your face. Somewhere, trillions of years later, that warmth will still glow in your blood. Joke break. Imagine trying to roast marshmallows at the surface of one of those first stars. 1, you'd vaporize instantly. 2, the marshmallow would vaporize faster, and 3, you'd never get the stick close enough, which is frankly the biggest tragedy here. As you let the thought fade, remember, the night sky above you is a fossil record. Every twinkle is a museum piece, a reminder that hydrogen and helium once gathered, stumbled, and finally caught fire. You, the quiet traveller in bed, are watching an ancient play that began long before Earth itself existed. You're still floating in that newborn cosmos, where the stars have just begun to flicker into existence, and the stage is set for the real drama. What started as hydrogen mist now begins to clump and crush, and here comes the slow, irresistible grip of gravity. You can almost feel it tugging at you too, like the universe itself is trying to pull you in for a hug, except this hug never lets go. The simplest way to picture it is to imagine dropping a marble into a mattress. The fabric sags, and more marbles roll toward the dip. That's gravity in action. Except, in space, the mattress isn't fabric, it's space-time itself bending under the weight of matter. Every atom of hydrogen has a say, whispering, "Come closer, come closer." Over millions of years, enough atoms heed the call until they gather into a dense ball. If you squint, you can almost see them swirling, like soap bubbles colliding in slow motion. The airless silence makes it deceptive. You expect noise, like the roar of a fire or the crash of waves. Instead, there's nothing, just absolute stillness, broken only by the invisible tug inward. If you were floating nearby, your hair wouldn't even sway. But at the centre of those gathering clouds, pressure mounts. The weight from all sides squeezes the middle tighter and tighter. It's like sitting at the bottom of a very deep pool, but instead of a few meters of water above you, you've got millions of kilometers of gas pressing down. Historians still argue whether the very first stars formed in neat giant swarms called population 3 clusters, or whether they showed up as loners. Either way, the principle is the same. Gravity wins. It always wins, patiently folding the universe into knots. You could say gravity has the personality of that one persistent friend who keeps texting, "You up?" Eventually the answer is yes. As the gas condenses, it heats up, just like your hands when you rub them together. You wouldn't expect clouds to get warm, but these cosmic clouds glow redder and hotter the more they collapse. At first, the heat isn't enough to spark fusion, but the pressure builds steadily, like a tea kettle beginning to whistle. Protostars emerge, still shrouded in their dusty cocoons, their light faint, their destiny sealed. There's a quirky tidbit here. Modern astronomers have observed stars being born inside elephant trunks, towering, finger-like pillars of gas shaped by nearby stellar winds. They look uncannily like giant cosmic fingers wagging at you, as though the universe is saying, "Don't forget where you came from." The most famous are in the Eagle Nebula, the Pillars of Creation, which Hubble turned into a desktop wallpaper for half the planet. Now, gravity has 2 jobs in this act. First, it brings the gas together, like rolling cookie dough into a ball. Second, it cranks up the pressure inside until the core becomes hot enough for fusion. This process can take millions of years, which sounds long, but in cosmic terms it's a blink. You blink once, and the cloud has gone from lazy mist to roaring furnace. The funny thing is, if you were a bystander during this collapse, you might not see much. Most of the heat and light are hidden behind dust. Only once the protostar clears its surroundings does it shine brightly, like a lamp finally uncovered from a blanket. And once it shines, it stabilizes into what astronomers call the main sequence, the star's long, steady adulthood. For perspective, our own sun has been in that phase for about 4.6 billion years, and it has at least another 5 billion to go. That's a whole lot of Tuesdays. A fun historical fact. It wasn't until the early 20th century that astronomers plotted stars on the Hertzsprung-Russell diagram, realizing that their brightness and temperature weren't random, but followed a clear pattern. That diagram is basically the family photo album of stars, showing who's young, who's middle-aged, and who's burning out dramatically. Here's the joke you didn't ask for but are getting anyway. If gravity were a person, it would be the strict gym coach who insists you keep doing squats forever. Lower, lower, hold it, don't stop. And just like in the gym, the result is a core of steel, or in this case, fire. As the collapse continues, you can almost hear the atoms protesting. Each hydrogen nucleus, a tiny proton, is like someone trying to hold its personal bubble at a crowded concert. Gravity doesn't care, it shoves them closer, And once they're packed tight enough, fusion begins. It's the universe's first spark of chemistry, and the real show starts from there. But for now, you stay in this quiet, breathless moment, watching a star cross the threshold. From a dark, whispering cloud to a blazing ember, it all comes down to gravity's squeeze. Without that invisible pull, hydrogen would still be drifting alone and you would never exist. The furnace has finally caught. You hover near the blazing heart of a young star, where hydrogen nuclei collide in endless, furious dances. Out here at the surface, you see only steady light, calm, golden, reliable. But deep inside, the core is chaos. Temperatures climb past 15 million degrees, and the pressure is so fierce it makes even the bravest atoms surrender their boundaries. This is fusion, the heartbeat of the cosmos. You can almost picture it in slow motion. 2 hydrogen nuclei, each a single proton, drift close. Normally they'd repel each other, like 2 people who both insist on taking the aisle seat. But inside the stellar core, gravity's squeeze has stripped away excuses. They're rammed together until the strong nuclear force, a kind of cosmic glue, snaps them into one. Suddenly they've formed deuterium, a heavier isotope of hydrogen. More collisions add more protons, and helium is born. Every one of those reactions releases a tiny bit of leftover energy, like change rattling out of your pocket. That change is light. Gamma rays at first, brutal and sharp, but softened as they bounce around for thousands, even millions of years before reaching the surface. When you see sunlight spilling through your window in the morning, you're looking at energy that began its journey long before humans existed. Historians still argue whether it takes 10,000 years or a million for a photon to escape the solar interior, but either way, you're basically bathing in ancient light. Fusion is a delicate balance. Gravity presses inward relentlessly, while the outpouring of energy pushes back. The result is a stalemate, like 2 kids arm wrestling endlessly, never quite winning. That balance keeps the star stable for billions of years. The star doesn't collapse, and it doesn't blow apart. It just shines. Here's a quirky tidbit. The sun fuses about 600 million tons of hydrogen into helium every second. Let that sink in. Every second. Yet the sun has enough fuel to keep going for billions of years. It's like watching someone burn through a mountain of firewood and realizing they still have a whole continent stacked behind them. If you lean closer, you can sense the rhythm. Each reaction is too small to see, but together they create a steady pulse, a kind of cosmic drumbeat. Some stars even literally pulse. Variable stars swell and shrink in brightness, their fusions beating like a slow breath. It's as if the universe itself inhales and exhales through these shining lungs. Back on Earth, it took scientists an embarrassingly long time to figure this out. In the 19th century, people assumed the sun burned like a giant coal furnace. The math, though, was brutal. At that rate, it would have gone dark in a few thousand years. That didn't sit well with geologists who were already talking about Earth being millions of years old. The mismatch sparked endless debates until fusion entered the picture in the 20th century, solving the puzzle elegantly. Sometimes science is basically just one long group text argument across disciplines. Now here's your joke for the night. Fusion is just atoms doing trustfalls. Hydrogen says, "Catch me." Helium forms. And the star responds, "Don't worry, I got you," for a few billion years. It's easy to forget that everything around you, your bones, your chair, even your favourite midnight snack, exists because stars figured out this balancing act. Without fusion, the cosmos would be a cold soup of hydrogen and helium, endlessly dull. Instead, stars shine, and in their hearts they forge the first steps toward complexity. You drift away from the stellar surface, carrying the warmth with you. That warmth has no edges, no borders. It's an infinite invitation. Somewhere, countless other stars are doing the same thing, humming in unison. And in their quiet, invisible forges, helium builds up grain by grain, the foundation for every heavier element to come. The stage is set, the recipe begun. Hydrogen into helium, energy into light, darkness into brightness. The heartbeat of fusion continues, steady, patient, eternal. You drift gently toward a familiar glow, a medium-sized star nestled in a quiet corner of the Milky Way. It's not the biggest, not the hottest, not the most dramatic, but it happens to be ours, the sun. For billions of years it has been cooking steadily, a cosmic kitchen operating without rest or complaint, and tonight you're allowed to peek over the counter. From a distance it looks calm, almost boring, like a round lamp hung in the sky. But you know better. Beneath that glowing surface, fusion roars. 4 hydrogen atoms combine into 1 helium atom, and the leftovers, those spare scraps of mass, turn into energy. That energy travels outward, bouncing like a pinball through a dense thicket of plasma. It takes thousands of years to crawl from the core to the surface, then just 8 minutes to sprint across space to Earth, slap your skin as sunlight, and remind you to wear sunscreen. Historians still argue whether ancient cultures understood that this warmth was truly the same energy, radiating from a distant sphere, or whether they thought the sun itself was a living, thinking deity. But either way, they worshipped it with good reason. Here's a quirky tidbit. The sun isn't perfectly round. Because it spins, it bulges very slightly at the equator, almost like a lazy balloon sagging a bit in the middle. You'd never notice from Earth, but the universe doesn't believe in perfect circles, just near misses. You hover closer, and the surface boils with convective cells. Imagine a pot of soup, bubbles of hot liquid rising while cooler blobs sink back down. Except this soup is made of ionized gas, and the bubbles are bigger than continents. Each one churns over minutes and hours, carrying energy from the interior toward the light we see. If you could put your ear to the sun, not recommended of course, you'd hear a kind of music, the vibrations of its surface resonating like a drum. Scientists actually study these oscillations in a field called heliosismology, listening for the star's hidden rhythms. The outer layer, the corona, stretches like a wispy halo, delicate and ghostly. During solar eclipses, it suddenly reveals itself, a crown of silver fire. Ancient people thought eclipses were terrifying omens. Some cultures banged drums to scare away the creature eating the sun. Now you just put on a pair of goofy cardboard glasses and Instagram the whole thing. Progress. The sun's steady kitchen also has its outbursts. Every so often, magnetic fields twist and snap, launching solar flares and coronal mass ejections into space. These storms can knock out satellites, disrupt GPS, and paint Earth's skies with auroras. Imagine if your oven occasionally hurled flaming spaghetti across the room. That's the sun's mood swings for you. And yet, for all its drama, our star is shockingly stable. Stars more massive than the sun burn bright and die young. Smaller stars burn dim but may outlive everything. The sun sits in the Goldilocks zone of stellar life. Not too hot, not too cold, just right for billions of years of quiet fusion. Without that patience, Earth would never have had time to form oceans, continents, or you, lying in bed listening to this. Here's your joke for the evening. The sun fuses hundreds of millions of tons of hydrogen every second, and it still hasn't burned out after billions of years. Meanwhile, you run out of energy halfway up the stairs. It's okay, you and the sun are just on different training schedules. A historical fact worth savouring. In 1610, Galileo tilted his crude telescope toward the sun and discovered sunspots, dark blemishes sliding across its face. Many refused to believe him, insisting the sun was perfect, untarnished. Yet those spots were the first hints that our star had a restless magnetic personality. Even in science, denial can shine brighter than evidence, for a while. Now, as you float back, the sun's light washes over you. It's steady, golden, reassuring. Every bite of food you eat, every breath of oxygen you take, every spark of life on Earth is powered by this quiet kitchen. Hydrogen turns to helium, and in the process, the sun keeps the recipe for existence going, one fusion at a time. You close your eyes, letting its warmth settle deep in your chest. The sun doesn't roar at you, doesn't demand attention. It just shines, endlessly, faithfully, humming along in the background of your life like the world's oldest appliance, one you never unplug. You leave the gentle warmth of our sun behind and drift deeper into the galaxy, where stars don't bother with moderation. Out here, massive stars sprawl like heavyweight champions, their furnaces blazing at impossible temperatures. If the sun is a steady kitchen stove, these giants are industrial blast furnaces stacked to the ceiling, cooking multiple courses all at once. At first glance, they look similar, bright, round, glowing. But you soon notice something different. Their light is bluer, sharper, like the glare of a welding torch. That blue hue means their surfaces burn much hotter than the sun's. and inside the difference grows even more extreme. The pressure at their cores is so intense that fusion races ahead, gobbling hydrogen at a reckless pace. Instead of billions of years, these stars live for only millions, a cosmic sprint compared to the Sun's leisurely marathon. Historians still argue whether the first massive stars burned alone, lighting up isolated pockets of the young universe, or whether they always gathered in clusters. Either way, they were crucial, because only these giant furnaces could begin layering the universe with elements heavier than helium. They're the loud, short-lived chefs who make sure the pantry is stocked. Here's where it gets fascinating. In massive stars, fusion doesn't stop at helium. Once the core runs low on hydrogen, gravity once again squeezes the star tighter. Temperatures soar, and helium nuclei collide to form carbon. Soon after the star gets creative, carbon fuses into neon, oxygen, and magnesium. Shell after shell of burning layers builds up like an onion. Hydrogen on the outside, helium deeper in, carbon below that, and so on, each layer fusing its own element, each zone hotter than the last. If you could slice a massive star in half, which you can't, unless you're wielding some kind of sci-fi lightsaber, you'd see this concentric structure, a cosmic layer cake of elements. A quirky tidbit: the short lives of massive stars mean some of them die young, exploding before nearby planets even finish forming. Imagine trying to move into a new neighborhood, only to have your neighbor's house explode in fireworks a million years later. Cosmic real estate is not for the faint of heart. But back inside the furnace, things are moving fast. Where the sun takes billions of years to burn through hydrogen, a massive star devours its hydrogen in just a few million. Helium burning, carbon burning, neon burning, each stage lasts less time than the one before. By the time it reaches silicon fusion, the star is counting down in days. It's like watching a speeding train, each stop shorter, each whistle louder, until the track simply runs out. To imagine the energy, think of this. Every second, a massive star releases more power than billions of nuclear bombs detonating at once. And yet, it doesn't explode right away. The balance of gravity and fusion still holds, for a while. A historical nugget: in the mid-20th century, the famous Burbage team, with Fred Hoyle, Margaret Burbage, Geoffrey Burbage, and Willie Fowler, worked out how elements were built inside stars. Their paper became legendary, though for years Margaret Burbage's contribution was overlooked simply because she was a woman. It's a reminder that even when stars play fair, humans don't always. And now, your light joke. If you think doing the dishes after dinner is exhausting, imagine being a massive star juggling 6 or 7 fusion reactions at once. Honey, did you remember to fuse the neon layer? As you drift away, you feel the sheer urgency of these stellar giants. They don't have time for subtlety. They live bright, they burn fast, and they set the table of the universe with new elements. Without them, there'd be no oxygen to breathe, no carbon to build life, no silicon to etch your phone screen. The sun may be our steady cook, but these bigger stars are the flamboyant chefs, throwing sparks and heat, layering the cosmic menu in record time. Their kitchens won't stay open for long, but oh, the meals they prepare while they last. You drift closer to the glowing heart of a massive star, where the kitchen has gotten inventive. The hydrogen and helium courses are done, and now the chef turns to something richer, more complex: carbon. Without this quiet, unassuming element, there would be no trees, no animals, no pizza crust, no you. And the way it's made is surprisingly tricky, almost like the universe playing dice. Inside the furnace, 3 helium nuclei, each just 2 protons and 2 neutrons, collide. Normally, the odds of 3 particles smashing together at once are laughably low. Imagine trying to juggle 3 flaming marshmallows while blindfolded in a wind tunnel. Yet at the temperatures and densities in a stellar core, helium atoms are packed so tightly that every so often they manage it. 2 helium nuclei form beryllium-8, but it's unstable, falling apart almost instantly, unless, that is, a 3rd helium nucleus barges in just in time, sticking the pieces together. When that miracle happens, carbon-12 is born. Astronomers call this the triple alpha process, but you can just think of it as the universe's favourite 3-body problem. Historians still argue whether Fred Hoyle's bold prediction of a special resonance state in carbon was an act of sheer genius or sheer luck. Back in the 1950s, he insisted that for life to exist, carbon must have a particular energy level that made the triple alpha process more efficient. Experiments later confirmed he was exactly right. Without that quirk, carbon would be rare, maybe non-existent, and we wouldn't be here to debate it. Here's a quirky tidbit. Carbon is the ultimate social butterfly. It can form long chains, rings, lattices, and practically infinite combinations with other atoms. That versatility is why it became the backbone of life's chemistry. You're basically a walking, talking carbon art installation. Imagine floating beside the star as carbon builds up in its core. Each atom is a tiny survivor of impossible odds, a success story against the chaos. The helium ash left over from hydrogen burning has now transformed into the very element that makes up your bones, your DNA, even the graphite in your pencil. You might picture the star like an enormous blacksmith's forge, sparks flying as it hammers helium into sturdier shapes. But the story doesn't stop at carbon. With the fire still blazing, helium can fuse with carbon to form oxygen. Add another helium nucleus, and neon appears. The kitchen is getting crowded, and the recipes are getting fancier. Still, it all begins with that delicate triple alpha step. Without it, the menu of existence would be tragically short. A historical fact worth savouring. Carbon wasn't just a scientific curiosity. Ancient humans unknowingly revered it too. Charcoal drawings on cave walls, diamonds admired as symbols of eternity, soot from fire pits, all forms of carbon, all reminders that this element has always been central to our story. And because we promised a joke every 1,000 words, carbon is like that one friend who shows up at every party. In water? Yep. In food? Definitely. In the air as carbon dioxide? Of course. It's the ultimate guest. Sometimes fun, sometimes overstays its welcome, but absolutely essential. As you let the thoughts sink in, you realize you're literally stardust. The carbon atoms in your fingertips were once fused in a massive star's fiery core. Long after that star exploded, those atoms drifted, joined a planet, became part of life, and eventually arranged themselves into you. All from 3 helium nuclei deciding, let's stick together. You float in the warm glow, carbon forming quietly beneath you. It doesn't shout, doesn't dazzle, but it changes everything. Without it, the universe would be sterile. Hydrogen seas, helium deserts, endless emptiness. With it, there's poetry, biology, love notes, laughter. The star doesn't know what it's making, but you do. The star's core keeps climbing in temperature, and with every tick upward on the cosmic thermostat, new elements begin to appear. You hover nearby, and the atmosphere feels like walking into a kitchen where every stove burner, oven and toaster is running at once. The star is no longer just a chef, it's a whole restaurant chain operating in overtime. After carbon comes oxygen, born when carbon nuclei fuse with helium. Then neon appears, then magnesium, then silicon, all in rapid succession. The process is called shell burning, and it stacks elements in layers like an onion. From the outside, you'd never know. The star still shines serenely, but inside it's a multitasking frenzy. Hydrogen still burns in an outer shell. Helium burns just beneath that. Carbon below, then oxygen, neon, silicon, all glowing in concentric rings, each hotter and denser the deeper you go. You picture peeling the star open like fruit. Each layer is a different flavour, arranged neatly. The outer hydrogen shell tastes like simplicity. The helium layer is sweeter. Carbon's layer is smoky. Oxygen feels crisp, like biting into winter air. Silicon, dense, metallic, sits at the core waiting for its final transformation. You can almost imagine a cosmic sommelier describing this onion of fire with unnecessary flair. Historians still argue whether the onion model of stellar structure oversimplifies the truth. Stars are messy in reality. Convection mixes layers, turbulence stirs the pot, magnetic fields disrupt order. But as a bedtime story, the onion metaphor works beautifully. Layers of fire cooking the universe's pantry. Here's a quirky tidbit. Some neon atoms in massive stars don't just fuse, they photodisintegrate. That's when a high-energy gamma ray smashes into the nucleus, breaking it apart. It's like cooking with so much heat that instead of baking bread, your oven decides to unbake it back into flour. Only stars could be so reckless. The fusion speeds accelerate wildly. Hydrogen burning lasts billions of years, helium hundreds of millions, carbon burning 1,000, neon burning just about a year. Oxygen burns for months. Silicon, mere days. It's like watching a movie on fast forward, the tempo increasing until you can barely keep up. In these furious last stages, neutrinos stream out by the trillions every second. They're ghostly particles so tiny and aloof that they slip through matter like it isn't there. Right now, billions are flying through your body without you noticing. You're basically a neutrino playground, though sadly they don't stop to pay rent. Let's slip in tonight's joke. If stars are like onions, then explaining them is like cutting onions. You always end up crying. Not from emotion, just from realizing how much math is involved. A historical nugget. In 1938, Hans Bethe worked out the nuclear processes that power stars, earning a Nobel Prize for the effort. But it wasn't just math. Bethe later used his expertise in nuclear physics to help design weapons during World War II, a reminder that the same knowledge can illuminate or destroy depending on how it's wielded. Meanwhile, back in the stellar kitchen, silicon burning creates iron, and that's where the road stops. Iron is a wall fusion can't pass, at least not in the normal way. The star, once so productive, is nearing exhaustion. It doesn't know it yet, but every layer, every frantic round of fusion, is rushing it closer to collapse. You hover in awe, watching this elemental symphony unfold. Carbon, oxygen, neon, silicon. Their notes blend together in the star's final performance. Each fusion reaction is a step in the choreography, each layer a stage prop. The show won't last long, but the echoes will shape galaxies. For now, though, the music continues. The shells burn, the onion layers thicken, and the star shines outward, unaware that the curtain is already beginning to fall. You sink deeper into the blazing furnace, past the outer shells of hydrogen and helium, through carbon and oxygen, until you reach the very heart. Here the pressure is unbearable, the temperature staggering. Fusion races along at a desperate pace, silicon atoms smashing together to form iron, and then everything halts. Iron, the cosmic roadblock. For billions of years, stars have built heavier and heavier nuclei by fusing lighter ones together. Each fusion released energy, fueling the light that made galaxies sparkle. But iron is different. When you try to fuse it, instead of releasing energy, it absorbs energy. Imagine trying to run a business where every transaction costs you money instead of making it. The star suddenly has no profit, no way to pay gravity back for its relentless pull. Historians still argue whether the very first observers of supernova remnants truly understood this dead-end role of iron, or whether they simply marveled at the beautiful wreckage in the sky. But today we know, once iron builds up in a star's core, collapse is inevitable. Here's a quirky tidbit. Your body already carries this signature of stellar exhaustion. The hemoglobin in your blood binds oxygen using iron atoms at its center. Without those ancient iron cores forged in dying stars, your blood wouldn't be red, and your lungs would be very disappointed in their career choice. The star, meanwhile, is struggling. The iron core grows heavier, pushing outward against layers still fusing like mad. But with no energy payoff from iron, there's nothing to counteract gravity. The core contracts, atoms crammed closer than ever before. Electrons are squeezed into protons, forming neutrons and releasing a flood of neutrinos. The star begins to buckle inward at unimaginable speeds. For a while it looks deceptively calm. From the outside, the star may still shine peacefully, unaware of its own looming doom. But inside, the balance has snapped. The furnace has hit the cosmic wall. Imagine the silence in that moment. A kitchen gone cold, the burners finally out, pots clattering empty. The star has cooked everything it can, stacked every layer possible. Carbon, oxygen, neon, silicon, they all had their chance. But with iron, the recipe stops. Here's your joke. Stars can fuse almost anything. Helium, carbon, silicon. But when they get to iron, they just say, nope, we're done. This menu has too much metal. A historical fact. In the 20th century, Walter Baade and Fritz Zwicky first described supernovae as the catastrophic collapse of massive stars into neutron stars. Their insight tied together the dead end of iron with the most spectacular explosions in the universe. Back then, many colleagues dismissed their ideas as too wild, but time, telescopes, and physics proved them right. As you hover, you can sense the suspense. The star's core is now a ticking bomb, iron piling up second by second. No fusion means no support. No support means collapse. The beautiful onion layers above don't realize their foundation is gone. You pause in that heartbeat of stillness, feeling the weight of inevitability. Iron, stubborn and unyielding, has closed the door. The star, once a majestic architect of elements, now waits on the edge of disaster. And though it doesn't know it, the greatest transformation is about to begin. The silence doesn't last. One moment the star is holding itself together, its iron heart swelling under unbearable pressure, and the next, it collapses. Gravity, patient for millions of years, suddenly seizes victory in less than a second. The core implodes, shrinking at a speed you can hardly imagine. If you blink, you miss it. At first, the outer layers don't even realize what's happening. They're still burning happily in their shells, hydrogen and helium fusing away, oblivious to the betrayal beneath them. But the iron core, crushed by its own weight, gives way. Protons and electrons slam together, creating neutrons. The matter is squeezed so tightly it's like stuffing the mass of the sun into a sphere the size of a city. The density rises to that of an atomic nucleus, something your mind isn't really designed to grasp. And then comes the rebound. The collapsing core slams to a halt and bounces outward, sending a shockwave racing through the star's layers. Neutrinos pour out in unimaginable numbers, streaming into space, billions upon billions passing straight through you right now unnoticed. Some crash into the star's outer layers, feeding the shockwave, powering the detonation. The star rips itself apart. A supernova. If you were floating nearby, don't worry, you wouldn't survive the light show, but let's suspend disbelief. You'd see the star's surface tear open in a storm of fire brighter than entire galaxies. For weeks, maybe months, the explosion outshines billions of other stars combined. It's the universe's loudest firework, a death cry so bright it can be seen across space. Historians still argue whether the guest stars recorded in ancient China and Korea, bright lights that appeared suddenly in the night sky and lingered for weeks, were supernovae or comets. The best evidence points to supernovae, like the one that created the Crab Nebula in 1054, still glowing in telescopes today. Here's a quirky tidbit. The Crab Nebula's remnant is still expanding at over 1,500 kilometers per second. Astronomers can literally watch the cloud grow, like cosmic slow-motion fireworks that have been going on for nearly 1,000 years. Back in the supernova's heart, the chaos is more than just destruction. This is where new elements, beyond iron, are forged. The extreme conditions slam nuclei together in ways normal fusion cannot, scattering gold, uranium and dozens of other heavy elements into space. The explosion is not just an ending, it's a creation, a seeding of the cosmos with riches. Here's your joke for tonight. Supernovae are basically stars throwing the ultimate tantrum. I can't fuse iron anymore. Fine, I'll just blow myself up and cover the galaxy in glitter. A historical nugget. In 1987, astronomers witnessed a supernova in the Large Magellanic Cloud, SN 1987A, the closest one seen in modern times. For months, telescopes around the world turned toward it, and detectors even picked up a burst of neutrinos just before the explosion was visible. It was the first time humanity caught both the light and the ghostly particles from a star's death, confirming theories that had lived on chalkboards for decades. You float in the debris, sparks of glowing gas swirling past you. The shockwave carries dust and atoms outward, scattering them across interstellar space. Every grain, every fleck is a seed for future planets, future oceans, future lives. The star is gone, but its ashes have written the next chapter. For a moment, you just watch the light bloom. The supernova is too bright to look at directly, but in this dreamlike drifting, it feels more like a sunrise than a catastrophe. Something ends, something begins. The cosmos once again recycles itself. The light from the supernova still dazzles behind your eyelids when you realize the real treasure isn't the explosion itself, it's what comes spilling out of it. Gold, platinum, uranium and other heavy metals, all whipped into existence in a frenzy of nuclear chaos. You're floating in the glitter storm of the cosmos' greatest alchemy trick. During the collapse, the star's core becomes an arena where neutrons fly at nearly the speed of light, smashing into iron nuclei before they can decay. This is the rapid neutron capture process, better known as the R process. It's like speed dating for protons and neutrons. Hi, nice to meet you. Boom, we're a heavier element now. The process happens so quickly and so violently that within seconds the periodic table fills up with metals too heavy for normal fusion to ever dream of producing. Historians still argue whether supernovae alone can account for all the universe's gold, or whether another, rarer process is needed. Some models suggest supernovae struggle to create enough of the heaviest elements, leaving room for neutron star mergers to share the credit. The jury's still out, which means your wedding ring might be a gift from a supernova, or from something even stranger. Here's a quirky tidbit. Every ounce of gold on Earth, from ancient coins buried in shipwrecks to the fillings in your teeth, was forged in one of these cosmic disasters. Next time you glance at a gold necklace, remember it was born in a fire so bright it outshone galaxies. You're literally wearing Stardust jewelry. In the expanding debris cloud, you can see the raw materials swirling. Oxygen will someday find hydrogen to form water. Carbon drifts, ready to become the backbone of life. But scattered here and there are flecks of gold and uranium shimmering like cosmic confetti. They don't look like much yet, just glowing atoms rushing through the void. But give them time, give them gravity, and they'll end up in mountains, rivers, even power plants. A historical nugget. When the Spanish conquistadors hauled tons of gold from the Americas back to Europe, they had no idea they were carrying the ashes of dead stars. Entire empires rose and fell on the wealth of supernovae, though no one at the time could have imagined the true origin of their treasure. And here's tonight's joke. People say money doesn't grow on trees, but technically it comes from exploding stars, so it's even harder to farm. The beauty of the R process is how reckless it is. Normal fusion builds elements step by step, patiently. The R process just hurls neutrons around until magic happens. Uranium, thorium, platinum, all formed in seconds, flung outward to drift for billions of years before finding a home. Some of those atoms, after endless wandering, ended up inside Earth's crust, fueling the radioactive decay that helps keep the planet's core molten. Without them, plate tectonics might not work and life might never have found stable ground. You float through the glowing wreckage, dazzled by the richness of it all. It's strange to think that something so violent could be so generous. The star has destroyed itself, yet in its destruction, it has written the recipe for planets, oceans, jewelry, and bones. The supernova fades slowly, its brilliance dimming over weeks and months. But the metals remain, scattered across the galaxy, silent promises of future worlds. The blast was the finale of one star's life, but the beginning of countless others. As the glow recedes, you realize you're surrounded by wealth, not the kind you keep in a bank, but the kind you carry in your body, the kind you walk on, the kind you admire in the night sky. The process is finished here, but its legacy has only just begun. The supernova's fireworks fade behind you, but the universe has one more forge up its sleeve, stranger, denser, and even more extreme. You drift through the quiet aftermath of stellar death until you find two tiny, brilliant embers spiraling toward each other. They look almost harmless, like glowing pearls in the darkness, but don't be fooled. These are neutron stars, and their dance will end in one of the most violent collisions in the cosmos. Neutron stars are what's left when a massive star's core collapses and squeezes protons and electrons into neutrons. Imagine cramming the sun's mass into a ball barely 20 kilometers wide. That's smaller than a city, yet heavier than everything you can picture. If you somehow scooped a teaspoon of a neutron star matter, it would weigh about as much as Mount Everest. Talk about dense cooking. As the two neutron stars spiral closer, their gravity distorts space itself, rippling it like a trampoline. You can feel the faint hum of gravitational waves, stretching and squeezing reality around you. Historians still argue whether Einstein truly believed anyone would ever detect these waves when he predicted them in 1916, or if he thought they were just elegant math with no practical hope. A century later, in 2015, scientists proved him right, catching the waves from a black hole merger, and in 2017 they did it again, this time from colliding neutron stars, confirming what you're watching now. Here's a quirky tidbit. The neutron star collision in 2017, called GW 170817, produced so much gold that astronomers estimated it was worth more than Earth's entire economy. Somewhere an intergalactic banker sighed happily. The two stars close in, orbit shrinking with every heartbeat. The final seconds are frantic. The stars whirl around each other dozens of times per second, faster than a blender on its higher setting. Then, impact. The collision unleashes a burst of gamma rays, a jet of light so powerful it briefly outshines every galaxy in the observable universe. The shockwave throws debris across space, and within that maelstrom the R process works over time. Gold, platinum, uranium, whole mountains worth are created in moments. Here's tonight's joke. If you ever misplace your wedding ring, don't worry. It's not lost. It's just waiting to be remade in the next neutron star smash-up. The debris glows as it cools, creating what astronomers call a kilonova. It's dimmer than a supernova, but rich with heavy elements, its light tinted with the signatures of freshly minted metals. You can almost see the shimmering gold dust drifting like sparks from a firework, spreading across the galaxy. A historical fact. For centuries, alchemists on Earth dreamed of turning lead into gold. They mixed potions, whispered incantations, and wrote entire books about it. Yet the universe had been pulling off the trick all along, just not in laboratories, but in colliding corpses of dead stars. The irony is delicious. You hover in the glowing aftermath. Compared to the furious explosion of a supernova, this feels slower, more deliberate, like the careful pouring of molten metal into molds. But don't be fooled, it's still one of the most violent events nature can muster. The collision has not only forged treasure, but also sent ripples of gravity all the way across the universe, felt faintly on Earth by detectors more sensitive than you can imagine. The kilonova fades, its riches scattered, its light dimming. But the heavy elements remain, drifting in the interstellar medium, waiting for gravity to gather them again. Somewhere down the line, they'll sink into planets, oceans, and even your bloodstream. The gold in your jewellery, the uranium powering nuclear plants, the platinum in your electronics, all may have begun in an event like this. You leave the scene with a strange calm. Two tiny stars collided, obliterated themselves, and in the process seeded the cosmos with beauty. Destruction and creation, again and again. The universe's favourite cycle. The universe is littered now with the ashes of giants, dust, gas, metals drifting aimlessly through the dark. You follow the currents, watching those tiny particles of starlight scatter and cool. At first, they seem insignificant. Stray atoms of carbon, grains of silicate dust, droplets of iron and gold drifting like smoke in the wind. But given time, patience and gravity, these scraps will become soil, stone, and ocean. The interstellar medium is not empty. It's a faint fog stretched thin across light years, where stardust mingles with hydrogen and helium left from the Big Bang. You can almost smell it, sharp and metallic, though in truth it's odourless. Slowly the dust begins to clump. A wisp of gas here, a fleck of carbon there, pulled together by that same invisible tug that once birthed stars. Gravity has never lost interest in recycling. Historians still argue whether Earth's earliest building blocks arrived from local star explosions alone, or whether we also receive shipments from more distant supernovae and neutron star mergers. Either way, the evidence is written in every rock, every ocean, every tree. Here's a quirky tidbit. Some of the grains of dust in your body may be older than the sun itself. Tiny pre-solar grains, microscopic crystals of stardust, have been found in meteorites that landed on Earth. They're literal fossils of stars older than our solar system by billions of years, carried across time like notes from an ancient ancestor. As clouds of gas and dust collapse, they spin, flattening into disks. At the centre, a new star forms, blazing into life. Around it, the leftover dust clumps into planetesimals, then planets. You watch as stardust grains gather into rocks, rocks into worlds. Oxygen atoms join hydrogen, forming water that splashes across the newborn Earth. Carbon finds its way into organic molecules, the scaffolding of life. Iron sinks inward, anchoring the planet with a molten core. The metals forged in explosions now form the bones of mountains and the gears of magnetic fields. It's almost absurd. All the chaos of supernova, all the violence of neutron star collisions, now reassembled into something so calm as dirt underfoot, or clay in a potter's hand. The universe, once fiery, now kneads its elements like dough, preparing something gentler. A historical fact. In the 1950s, scientists studying isotopes in meteorites confirmed that many elements in our solar system came from ancient stellar explosions. Before that, some still imagined Earth's ingredients were unique, not shared with the broader cosmos. The discovery closed the gap, proving that your backyard soil has the same origin story as the brightest star in the sky. Here's tonight's joke. Stardust is everywhere. Which means, technically, when you're cleaning dust off your shelves, You're committing interstellar genocide. Don't feel too guilty. It'll settle somewhere else. As you float along, you realize how deeply personal this story is. The atoms in your breath have traveled across billions of years, through furnaces and explosions, through endless drifts of space, until they found one another again on Earth. You're not just made of stardust, you're made of recycled stardust, atoms that have lived many lives before yours. Some of the oxygen in your lungs might once have shimmered in the atmosphere of a long-vanished star. Some of the calcium in your bones might have formed in the fiery shell of a massive giant. The stardust settles, the disk spins, and planets coalesce. You hover over this cosmic pottery wheel, watching worlds take shape. The recipe isn't random. It's the legacy of generations of stars, each one giving a little more to the mix. And in the end, the dust of death becomes the soil of life. You drift downward now, past the crust of the newborn Earth, past the oceans just beginning to shimmer under the sun's glow, and into the planet's hidden heart. It's dark here, crushingly hot, and yet this is where one of the greatest gifts of the stars resides: iron. Forged in stellar deaths, it now forms Earth's metallic core, a colossal ball of mostly iron and nickel spinning silently beneath your feet. Imagine the moment of its birth. When Earth was still molten, heavy metals sank toward the centre, while lighter materials floated upward. Iron, plentiful from long-gone supernova, sank like an anchor. Over time it gathered into a sphere about the size of the moon, buried at the centre of our planet. That core is still there now, and though you'll never see it directly, you feel its influence every day. Historians still argue whether the exact distribution of iron in Earth's core came from a single massive supernova near the Sun's birthplace, or from multiple ancient explosions. What's clear is that without it, Earth would be a very different and less hospitable place. Here's a quirky tidbit. The Earth's core generates our magnetic field, which shields us from solar radiation and paints the sky with auroras. Without that molten iron dynamo spinning below, our atmosphere might have been stripped away long ago, leaving Earth as barren as Mars. Every compass you've ever used is essentially a tiny thank you note to dead stars. The core has two parts, a solid inner sphere and a liquid outer shell. The outer layer churns slowly, currents of molten iron moving like honey. That motion creates a geodynamo, producing the magnetic field that stretches outward, invisible yet vital. The inner core, though solid, is slowly growing as the planet cools, crystallizing iron atoms one by one. It's a process so slow you'd need billions of years to notice the change. A historical fact. In 1906, Richard Dixon Oldham analysed seismic waves from earthquakes and realised Earth must have a core distinct from the mantle. Later refinements showed it was metallic, not rocky. It took clever humans listening to the planet's own rumblings to confirm what supernova had already written deep inside it. And here's tonight's joke. If someone ever tells you you're cold-hearted, remind them your core is made of molten iron, spinning at thousands of kilometers per hour. That should settle the argument. As you float in this molten realm, you notice how central iron is not just to Earth's geology, but to you. The same element in the core runs through your veins. The iron in your blood binds oxygen and ferries it through your body. Every breath you take is a partnership between your lungs and the remains of an exploded star. You're walking around with tiny supernova relics in each red blood cell. The dual role of iron, planetary core, and human lifeblood ties you directly to the stars. Without iron, Earth might never have developed a protective magnetic field, and without iron, your body couldn't carry oxygen. You owe your existence twice over to the stubborn element that once ended a star's life. You pause here in the silence, letting the image form, a glowing iron heart at the centre of the world, pulsing steadily, protecting, sustaining. The same iron glints faintly in your blood under moonlight. Above, auroras flicker, painted by the invisible field born deep below. Everything connects, everything loops back to Stardust. The star may have died when it hit the wall of iron fusion, but in that death it gave Earth both strength and breath. You carry a piece of that core inside you, every second of every day. You rise slowly from Earth's glowing metallic heart, drifting upward through the mantle, through the crust, and finally back to the cool surface where oceans shimmer under a young sky. The water laps gently, as if whispering its own origin story. And yes, like the iron in your blood, like the carbon in your bones. These oceans too are gifts of stars. Follow the oxygen first. It was born in the furnaces of massive stars squeezed out during helium and carbon burning, then hurled into space during supernova explosions. Hydrogen, the simplest and most abundant element, was already everywhere, waiting patiently since the Big Bang. When the two finally met in the right conditions, oxygen from dead stars, hydrogen drifting in clouds, they clasped hands and formed H2O, simple, elegant, life's foundation. Historians still argue whether most of Earth's water arrived from icy comets and asteroids, or whether it condensed directly from the hydrogen and oxygen already swirling in the solar nebula. Either way, the truth is that the oxygen atoms in each droplet once blazed inside stars before cooling to settle on a rocky world. When you drink a glass of water, you're sipping liquid starlight. Here's a quirky tidbit. The average molecule of water on Earth has been recycled countless times. The glass you drink tonight may once have been part of a dinosaur's bloodstream, a glacier's core, or a medieval baker's sourdough starter. Water never truly leaves, it just changes costume again and again. You float above the young oceans, watching them fill basins carved by volcanic rock. Steam condenses, clouds gather, rain falls in endless curtains. Rivers carve their way to the sea, carrying minerals with them. Some of those minerals, salts, metals, and even traces of uranium were forged in long-dead stars. The ocean is not just water, it's a broth of cosmic history. A historical fact. In 1610, Galileo looked at the moon and saw dry, barren craters. People wondered if Earth's oceans were unique, or if other worlds might also carry water. It wasn't until recent decades, with probes discovering ice on Mars, Europa, and Enceladus, that we realized water is scattered throughout the solar system. The stars didn't just gift Earth. It seems they stocked the entire cosmic kitchen with the stuff. Tonight's joke, people say you should drink 8 glasses of water a day. Technically, that means 8 glasses of melted star every day. Suddenly, hydration feels like cosmic self-care. The oceans deepen, shimmering blue under the sun. They cradle new chemistry, amino acids assembling in tidal pools, life's first whispers bubbling from star-forged ingredients. The oxygen that once glowed inside a stellar furnace now dissolves in seawater, feeding the earliest microbes. Over billions of years, those microbes will release even more oxygen back into the air, reshaping the planet. It's a feedback loop that began with ancient stars and still flows through your every breath. You float gently above the waves, imagining the endless exchange. Clouds rise, rain falls, rivers flow, oceans churn. Each droplet carries the memory of its birth in nuclear fire. The water rocking against the shore is older than the continents it kisses, older than Earth itself. You close your eyes and listen. The waves crash softly, steadily, as though echoing the fusion heartbeat of the stars. The rhythm is the same, energy cycling, elements transforming, stories continuing. The stars didn't just give Earth fire and iron, they gave it oceans to cradle life. Every tide is a cosmic inheritance. You float above the oceans for a while, listening to their endless hush until the thought arrives like a quiet wave. Every part of you is built from those same stellar gifts. You are, quite literally, recycled starlight. The phrase isn't poetry, it's chemistry. Look at your bones. They're lattices of calcium, an element forged in massive stars during helium fusion. Each vertebra in your spine, every ridge of your teeth, carries the memory of that fiery process. Your muscles rely on sodium and potassium, more stellar hand-me-downs. Your nerves fire with the help of magnesium ions, also born in stellar furnaces. And at the heart of it all, your blood glows red thanks to iron, the stubborn element that once marked the death of a star. Historians still argue whether Carl Sagan's famous line, "We are made of star stuff," was meant as poetic metaphor or literal fact. But modern astrophysics confirms it. Except for the lightest elements, nearly everything in your body was cooked in stars long before Earth existed. Sagan wasn't exaggerating, he was understating the case. Here's a quirky tidbit. Even the phosphorus in your DNA, the element that makes life's information storage possible, was born in stellar explosions. Without phosphorus, your genetic code couldn't exist, which means every thought you've ever had, every memory, every dream, is etched with the handwriting of long-dead stars. You stretch out, imagining your body as a constellation of elements: calcium bones, iron blood, carbon flesh, oxygen breath. You're a walking periodic table, arranged by biology but sourced from astronomy. Every cell is a shrine to stellar alchemy. A historical nugget: the philosopher Democritus in ancient Greece guessed that everything was made of tiny indivisible units he called atomos. He could never have known that those atoms were themselves forged in stars. Yet his intuition nudged humanity in the right direction. Long before telescopes, particle accelerators, or space probes could confirm it. Here's tonight's joke: if someone ever tells you you're ordinary, remind them you're made of carbon, nitrogen, and oxygen, the same ingredients that power supernovas. Ordinary? Please. You're cosmic haute couture. Even your breath is star stuff. The oxygen you inhale each second was born in stellar cores, while the carbon dioxide you exhale carries carbon forged in triple alpha fusion. With every inhale and exhale, you're reenacting the life cycles of stars, a miniature echo of the cosmos' grand performance. The more you notice, the more impossible it feels to separate yourself from the stars. They are not distant ornaments hung in the night sky. They are your ancestors. Their ashes became your bones. Their light became your warmth. Their elements became your laughter, your heartbeat, your fingertips brushing against the fabric of the world. You let the thoughts settle over you like a blanket. You're a story billions of years in the making. Stardust gathered, planets formed, oceans filled, life emerged, and now here you are, listening to this quiet tale under dim lights. The stars live on, not just overhead, but within you. The stars have left their fingerprints all over your body, but you're not the first to notice. Long before telescopes and particle accelerators, humans looked up at the night sky and tried to explain their connection to it. Myths, legends, and origin stories, these were humanity's first astronomy textbooks, poetic guesses at why the heavens mattered so deeply. You sit now around a crackling ancient fire, hearing voices drift across time. To the ancient Egyptians, the goddess Nut arched across the sky, swallowing the sun each night and birthing it anew each morning. In their myths, stars weren't just distant lights. They were the souls of the departed, shining eternally. Imagine how comforting it must have been to think your loved ones twinkled above you forever. The Greeks told a different story. They pictured constellations as frozen tales: Orion the hunter, Perseus with his sword, Cassiopeia in her chair. Every star a character, every cluster a reminder. The myths gave structure to the chaos, connecting human drama to the glittering patterns overhead. Historians still argue whether these constellations were more about navigation or storytelling, but perhaps both were true. Sailors needed maps, poets needed meaning. Here's a quirky tidbit. The Navajo saw the Milky Way not as a road of stars, but as a great trail of sparkling pollen, cast across the sky by holy people during creation. Even now, that image feels more nourishing than sterile physics equations. Across cultures, stars were woven into creation myths. In some Polynesian traditions, humans were formed from red clay shaped by the gods under the starlight. In China, the cosmic order was imagined as a great balance of yin and yang written in the heavens. In Norse myths, sparks from the primordial fire forged the sun, moon, and stars. Always, humanity saw itself reflected in the sky, long before science confirmed that reflection was literal. A historical nugget. In the 17th century, Johannes Kepler wrote not only about planetary orbits, but also about the music of the spheres, convinced that celestial bodies sang in harmony. He blended myth, faith, and mathematics into one worldview. He wasn't entirely right, but he wasn't entirely wrong either. Stars do hum with vibrations. Helioseismology proves it. Kepler was listening for a truth science would only later hear properly. Here's tonight's joke. If myths say stars are the souls of the dead, then the Milky Way is just the galaxy's most crowded group chat. As you drift in thought, you realize these ancient myths weren't so different from modern explanations. Both are attempts to answer the same haunting question. Where do we come from? The myths used gods and symbols. Science uses equations and telescopes. But the impulse is identical. Humans staring upward, feeling the pull of kinship with the lights above. You hover now between eras, the fire crackling at your back, galaxies swirling ahead. Whether through myth or astrophysics, the conclusion feels the same: you belong to the stars. Every culture whispered it differently, but all of them knew. The myths linger in your mind, but now you float forward into the age when humans began trading legends for equations. The question of where elements came from shifted from temples and firesides to laboratories and lecture halls. Yet even here, the answers didn't come easily. The history of stellar alchemy is full of rivalries, wrong turns, and debates so fierce you'd think the stars themselves were grading the papers. In the 19th century, many scientists believed the sun shone by burning coal or some similar fuel. The math didn't add up. At best, the sun would last a few thousand years. Geologists, pointing to ancient rocks, insisted Earth was far older. Historians still argue whether this mismatch fueled more polite collaboration or more frustrated shouting matches. Either way, it left everyone unsatisfied. Then came the idea of nuclear fusion in the early 20th century. Arthur Eddington boldly proposed that stars shine by fusing hydrogen into helium, releasing vast amounts of energy. It sounded wild at the time. No one had ever seen such reactions outside of theory. Critics scoffed, yet Eddington held firm, sketching the foundation of stellar physics years before experiments caught up. Here's a quirky tidbit. When Cecilia Payne, in 1925, argued that stars are made mostly of hydrogen and helium, her PhD examiners urged her to downplay the claim. It sounded too radical. But Payne was right, and her discovery is now considered one of the most important in astrophysics. The irony? Her work was initially dismissed by the very men who later accepted it. By mid-century, the great B2FH paper, Burbage, Fowler, Hoyle, stitched together the story of how stars forge elements. It explained hydrogen fusion in small stars, carbon and oxygen production in massive ones, and supernova seeding the rest. It was a masterpiece, but not without controversy. Fred Hoyle, brilliant and abrasive, often clashed with colleagues, sometimes undermining his own credit. Historians still debate how much recognition each member deserved, especially Margaret Burbage, whose role was often minimised. Here's tonight's joke. Astrophysicists arguing about nucleosynthesis is basically the universe's version of a cooking show. Everyone agrees the meal tastes great, but nobody can agree on who wrote the recipe. Nuclear physics also came with darker associations, the same discoveries that explained stellar fusion powered atomic bombs on Earth. Beth, Fermi, Teller, their names shine in both astronomy and weapons development. The stars offered beauty, but humans, as usual, found ways to weaponize the knowledge. Science rarely gives us one gift without a dilemma attached. Even now, debates rage on. Lithium, for instance, remains a puzzle. Models predict more of it should exist in the universe than we actually see. Did stars destroy it? Did we misunderstand its production in the Big Bang? No one is quite sure. You realize that not even the stars have given up all their secrets. You hover in this middle space between myth and certainty, between story and science. The human journey toward understanding hasn't been smooth, but it has always been relentless. From coal-burning theories to hydrogen fusion, from skepticism to Nobel Prizes, the thread runs straight, a refusal to stop asking. You drift now into the modern era, where telescopes and spectroscopes replace myths and hunches. If the universe is a crime scene, then astronomers are the detectives, and starlight is their fingerprint evidence. By studying it, they've learned exactly which elements stars are cooking, without ever stepping foot inside one. It all began in the 19th century, when scientists discovered that light, passed through a prism, separates into a rainbow. But that rainbow isn't smooth. It's scarred with dark lines, absences where atoms have absorbed particular wavelengths. Each element leaves its own unique barcode, a pattern of lines no other atom can fake. Historians still argue whether it was Fraunhofer in 1814 or later physicists who truly understood what those lines meant, but his name stuck. Fraunhofer lines, the fingerprints of the stars. Here's a quirky tidbit. Helium was discovered in the sun before it was discovered on Earth. In 1868, astronomers noticed a spectral line they couldn't explain. They named the mystery element helium after Helios, the sun god. Only decades later did chemists isolate it on Earth, confirming the cosmic detective work was spot on. With this tool, astronomers could suddenly read the universe like a library. They saw hydrogen and helium dominating, carbon and oxygen shining through, heavier metals whispering from deeper furnaces. Every star became a lab report written in light. The technique grew sharper with technology. Today, telescopes can record spectra from galaxies billions of light years away. By analysing them, scientists not only identify elements, but also measure motion, distance, and age. The cosmos has no way to hide its secrets. Every photon betrays its origin. A historical nugget. In 1929, Edwin Hubble used these light signatures to show that galaxies are racing away from us, expanding the universe itself. The discovery reshaped cosmology, all from squinting at starlight's fingerprints. Here's tonight's joke. Spectroscopy is basically karaoke night for atoms. Each one insists on singing its own unique note, and astronomers are just the poor audience trying to keep track of who's on the mic. You float above an observatory dome now, its telescope aimed upward, quietly drinking in starlight. Inside, computers decode the data, drawing colourful graphs of absorption lines. It doesn't look magical, just squiggly patterns on a screen, but it's the most direct proof we have of stellar alchemy. Those squiggles tell us where your oxygen came from, why your jewellery sparkles with gold, and how the universe has evolved for 13.8 billion years. Beyond the lab, the detective work has gone cosmic. Space telescopes capture spectra from exploding stars, confirming the fingerprints of heavy elements forged in the blast. Gravitational wave detectors pair with optical telescopes to catch the glow of neutron star mergers, their light stained with R-process signatures. It's like finally catching a thief not just from fingerprints, but on video too. You realise how elegant it all is. Humans, tiny and fragile, will never visit the core of a star. But by analysing its light, you can read its history as clearly as a diary. Every element leaves its mark. Every story shines through. The night sky isn't silent, it's a symphony, and spectroscopy is the sheet music. You drift in the glow of spectrographs and telescopes, but just when you think the cosmic cookbook is complete, the universe leaves you dangling. There are still mysteries, gaps in the recipe, puzzles that refuse to sit quietly on the shelf. Take lithium, for instance. According to Big Bang nuclear synthesis, the first minutes of the universe should have left behind a generous sprinkling of hydrogen, helium, and a pinch of lithium. Observations match beautifully for hydrogen and helium. But lithium? The numbers don't add up. There's far less of it in old stars than theory predicts. Historians still argue whether this lithium problem points to errors in measurements, quirks of stellar physics, or cracks in our understanding of the early universe itself. It's like baking a cake and finding the sugar missing, even though the recipe swears you put it in. Then there's the role of dark matter. Ordinary atoms, the kind forged in stars, make up only about 5% of the universe. The rest is invisible, detectable only by its gravitational pull. Did dark matter influence how stars forged the first elements? Does it still shape the chemistry of galaxies? No one knows. For now, it's the ultimate background character, always present, never explained. Here's a quirky tidbit. Some scientists have proposed that axions, hypothetical particles that could make up dark matter, might occasionally convert into photons inside stars. If true, stars wouldn't just forge elements. They'd also be secret factories for exotic physics we've yet to confirm. Even heavier mysteries remain. Did all of Earth's gold come from supernovae and neutron star collisions? Or are there rare, exotic processes we haven't seen yet? Some models suggest magnetorotational supernova, explosions turbocharged by extreme magnetic fields, could forge metals more efficiently than we thought. Others point to collapses, black hole-forming giants that might briefly act as element factories before swallowing themselves whole. The universe seems to enjoy keeping a few recipes off the public menu. A historical nugget. In the early 20th century, scientists were convinced the periodic table was nearly complete, with only a handful of missing elements. Yet as nuclear physics advanced, it turned out the table wasn't just filled, it was explained. Stars had written it long before humans discovered it. Today, the challenge isn't the missing boxes, but the unanswered how behind their origins. Here's tonight's joke. The periodic table is like IKEA instructions. You think you've got all the pieces, but there's always one screw, or one element, that just doesn't seem to fit where it should. You hover in this place of uncertainty, and instead of frustration, you feel comfort. Mystery is part of the universe's lullaby. If everything were solved, the night sky might lose some of its shimmer. The debates over lithium, the search for dark matter, the questions about heavy elements, they're invitations to keep looking, to keep wondering. The stars have already given you so much. Hydrogen for your water, oxygen for your breath, carbon for your cells, iron for your blood. Yet they also keep secrets, reminders that curiosity should never burn out. You let the thought sink in. The universe is both generous and coy, revealing and concealing, always offering just enough answers to keep you searching for more. The mysteries swirl behind you, but now the journey begins to quiet. You drift out past the galaxies, past the clouds of dust and the glowing nurseries, until the stars themselves seem to dim. Out here, in the stillness, the pattern becomes clear. Stars flare to life, they cook their elements, they collapse, they scatter, and the cycle begins again. Every atom you followed tonight is part of that eternal recycling program. Nothing is wasted, everything is reused. The hydrogen born in the Big Bang became helium in the first stars. Those stars forged carbon, oxygen, neon, silicon and iron, scattering them in supernovae. Neutron star collisions embroidered the cosmos with gold and uranium. Dust clouds gathered the remnants, knitting them into new stars, planets, oceans, and eventually you. Stars fade, but the elements remain. Historians still argue whether this recycling is truly infinite, whether the universe will always form new stars, or whether someday the fuel will run out, leaving only cold embers drifting in endless dark. For now though, galaxies still sparkle and the cycle continues. Here's a quirky tidbit. Some atoms in your body will survive longer than Earth itself. Long after the sun swells and engulfs our planet, the atoms of calcium in your bones and iron in your blood may still be drifting through the galaxy, waiting to join a new world. You're not just stardust, you're immortal in pieces. A historical nugget. When the periodic table was first arranged by Mendeleev in 1869, he couldn't have guessed that its elements told the story of the stars. His grid looked like a chemistry puzzle, but hidden within it was the autobiography of the universe. And here's the final joke for tonight. If stars are just recycling plants, then you're basically a very fancy piece of cosmic compost. The good news? Compost grows beautiful things. You pause here, letting the vastness settle over you. The stars don't feel distant anymore. They feel like family, loud, fiery, dramatic relatives who live far away but send gifts that shape your everyday. Every shimmer overhead is proof that the cosmos keeps giving, even in its endings. The truth is simple and calming. You are part of this cycle. The atoms that make you will scatter someday too, seeding another generation of stars, another world, another listener perhaps lying quietly in bed, wondering where it all began. The stars fade, the elements remain, and the story never ends. The journey through stars and stardust softens now, the pace slowing as though the universe itself is exhaling after its long, fiery tale. You let go of the explosions, the collisions, the blazing furnaces, and rest instead in the quiet truth beneath them. Everything recycles, everything flows onward, nothing is ever truly lost. The stars above you no longer dazzle with urgency. They glow gently, steady lanterns in a vast dark room. You imagine them dimming just slightly, as though turning down the brightness for sleep. Their heartbeat continues, but softly, like a lullaby heard through a wall. The images fade in long, calm strokes. The molten heart of Earth cools into stillness. Oceans smooth into mirrors, each wave folding gently into the next. The atoms in your blood quiet their restless movement, settling into silence. All the fiery chemistry of the universe folds itself into a single soothing truth. You're made of stars, and the stars are patient. Even the mysteries feel less like puzzles and more like gentle questions waiting for another day. The lithium problem, dark matter, the fates of galaxies, they can rest for now. They will wait. Tonight there is no need to solve, only to drift. So you lie back, the weight of stardust pressing softly into your pillow, your breath moving like a tide. The cosmos hums faintly around you, steady, kind, unhurried. And as the last light of thought fades, you feel the quiet cycle carrying you too, folding you back into its endless gentle rhythm. Sweet dreams.